Hello and welcome to an evolutionary analysis of software architecture smells. My name is Philipp Gnoyke and I have the honor of speaking for my colleagues Sandro, Schulze and Krüger to present you the results of our study, which was first written for the International Conference on Software Maintenance and Evolution. So let's get right into it. First, let's talk about the broad topic that we are focusing on, which is software quality. Why is software quality important and why should developers keep an eye on it on the long term? Well, in a nutshell, the value of a software product depends on whether it fulfills its requirements. To do so reliably, developers can aim to adhere to quality criteria. A well-known quality criterion is maintainability, which comprises aspects like, is the code in my system easily understandable, changeable, extensible, reusable, and testable? Adhering to these aspects is important to keep long-term maintenance costs low and allow the developer to adapt efficiently to evolving customer demands. That is, because systems have to undergo changes or become increasingly irrelevant according to Lehman's laws. Thus, the question is, how can developers ensure maintainability? A good idea is to follow best practice design principles and rules, which isn't always straightforward. One way of checking whether such a design principle has been violated instead of followed is to scan for so-called smells. Smells can appear on different levels of a system, including its architecture on the macro level. In this context, domains like dependencies, hierarchies, interfaces, and the modularization of functionality can be affected. In this study, we focused on three types of architecture smells that concern dependencies. These are hub-like dependencies, which represent a hub class with a high number of both incoming and outgoing dependencies. Cyclic dependencies, which break the acyclic dependency principle and can occur both among classes as well as packages. And third, unstable dependencies, in which a stable component is dependent on an unstable component. In this context, stability refers to the likelihood of changes occurring to a component. A related concept to smells, in order to summarize deviations from design principles, among other aspects, is technical debt. It can be introduced in different ways, such as by rushing the development of a new feature in order to reduce the time to market. However, by rushing and thus probably neglecting practices like refactoring, testing, or documenting, the code becomes less maintainable, which is linked to higher costs for further development in the future. This effect can be described as an interest rate of technical debt, which occurs as long as the debt is not reimbursed by refactoring and can, in the worst case, cause technical bankruptcy, i.e. the abandoning of a system, which is usually not something that you want to have as a developer. Similar to smells, technical debt can be identified in different domains, including architectural debt, which we focused on, or in other words, violations to best practice software architecture. Technical debt can be quantified, for example, by measuring the number and severity of smells. The result is usually referred to as a technical debt index. All right. After this broad introduction, let's look on why we performed a study in this field. So, architecture smells and especially code smells. Wait, that is blank. Interesting. Okay. Architecture smells and especially code smells have been subject to research for several years and in different domains. This includes aspects like the detection strategies and tools, the immediate impact of smells on software quality, and refactoring techniques in order to remove smells from the code. Considering that violated design principles affect the maintainability of software in the long term, it is especially interesting to analyze the evolution of smells. So in other words, how long do they persist? How do they change over time? And under which conditions are they introduced or removed? Furthermore, what exactly is the long-term impact of smells on software degradation? And especially, what is their long-term relationship with technical debt? These questions were evaluated in many studies for code smells, but to a considerably lesser degree for architecture smells. There is a study from 2019 by Sas, Averio, and Arceli Fontana who made a first advance into this topic. We want to expand on their techniques and findings. So, for this paper, we narrowed our study to three research questions that are the following. First, how does the number of architecture smells evolve over time? Second, what is the impact of architecture smells on technical debt? And third, what influences the lifespan of architecture smells? All of these questions stand under our overarching question, which is to what extent and under which circumstances do architecture smells contribute to software degradation? Before we look at our case study and the answers to these questions, I would like to give some details on new conceptual ideas that we introduced in order to better understand the evolution of smells. So, first of all, we found that the term smell itself can be ambiguous in the context of evolution, because it can both refer to a particular detected instance in a particular version of a system, as well as the overall existence of a smell over several versions, during which a smell can undergo considerable changes. For example, including more and more classes to its overall reach. That is why we propose to refer to a smell in a particular version as an intra-version smell, while referring to its entire existence as an inter-version smell. Inter-version smells consist of multiple intra-version smells if their lifespan is longer than a single version. By comparing intra-version smells with a matching or tracking algorithm, like for example already the study of Sass et al. Performed, their affiliation to inter-version smells can be identified. This conceptual division also helps to clearly distinguish different types of smell properties. For example, properties of related intra-version smells can be analyzed as a time series. What you are seeing in this picture is basically a one-dimensional sequence of related intra-version smells. We found that this one-dimensional pattern doesn't always have to be the case. For example, for cyclic dependencies. And I will now show you why. As you can see here, two separate cyclic dependencies can merge if additional dependencies are introduced between them. In this image, version B shows that the two previous cyclic dependencies merge together and are now forming a single uniform cyclic dependency, basically. And this means that every class in this graph can be reached from all other classes. The opposite effect can also happen if a certain dependency within a cyclic dependency is removed, which causes the splitting into multiple disjoint cyclic dependencies. Thus, if we want to show the evolution of intra-version smells over multiple version, we have to depict them as a graph in such a case. We have proposed the name cyclic dependency evolution graph in order to represent the evolution of cyclic dependencies in such a way. The consequence of that is that intra-version cyclic dependencies can have multiple predecessors in the same version, as well as multiple successors in the following version. Cyclic dependency evolution graphs are mostly simple, but we found that some of them can reach considerable sizes and complexity, like the one here at the bottom, with many branches, basically. So, now let's go from theory to practice and look at our study design. For detecting smells, we have employed the academic tool Archon, in which we modified the cyclic dependency detection, added the computation of additional properties, and included a slightly adapted technical debt quantification algorithm, which was originally devised by Roveda. Archon, in turn, is controlled by our own tool ASTDEA, which tracks inter-version smells and computes additional properties over the evolution of systems. In the end, we arrived at an output dataset from which we extracted statistics and trends. As input dataset, we selected the Qualitas Corpus evolution distribution, as it provides a diverse collection of established long-running systems. They range from 16 to 106 versions, with up to 485,000 lines of code per version that we could analyze for each system. So, how do our results look like? Disclaimer, given that I cannot ramble for an hour here, I only show you now a selection of our results. However, you can find a more extensive version in the paper itself and in the replication package. Considering that, considering our first research question, we found that the number of architecture smells and the code size correlated in most cases. Thus, we could not confirm exponential increase trends as they could be assumed, given that technical debt includes this interest rate metaphor, which you could also derive a compound interest rate metaphor from. Instead, we found that a considerable share of architecture smelts remained in the systems beyond the analyzed time span, which is also interesting. Of course, the number of architecture smelts alone does not give a full picture. Therefore, we can also relate it to the evolution of technical debt. Here we can see a much, again, I'm sorry that the slide is missing, at least for me. Here we can see a much higher variance between the systems, but also within the history of each system. Again, we could not identify exponential trends when looking at the relative levels of technical debt. Considering the debt's composition, cyclic dependencies among classes contribute the most in a majority of the analyzed systems. Interestingly, the share on technical debt of cyclic dependencies among packages and hub-like dependencies was considerably higher than their share on the number of architecture smelts in many systems. Okay, finally, let's look at our third research question, which is what influences the lifespan of architecture smelts? For cyclic dependencies among classes, we found that increasing numbers of affected components, increasing numbers of dependencies between them, and increasing numbers of simple subcycles among them resulted on average in increasing lifespans. Other considerable patterns were visible for unstable dependencies. They persisted increasingly longer if they were more central in the system, overlapped with other smelts, and were increasingly unstable. Okay. In our study, we explored novel concepts of viewing the evolution of architecture smelts and found interesting results. Among these are, first, the number of architecture smelts remains mostly stable compared to the code size of a system. Second, certain types of architecture smelts have a greater impact on system degradation. Third, certain properties determine how much an architecture smelt contributes to system degradation. Building upon this study, a future work that we are currently working on is to more closely analyze the evolution of the properties of individual smelts. All right. I'm keen to answer your questions either live right now or if you prefer later per mail. Thanks for your attention.